All right, welcome to Next Gen Manufacturing. Today, we are diving deep into an invisible force that can make or break even the most advanced machining operation, heat. It's there with every single cut, and look, getting it under control isn't just a small improvement. It's the secret to unlocking truly next-generation performance. So let's jump in and see how you can master it.
Okay, let me ask you something. I want you to picture one of those incredible, high-performance cutting tools, made of super tough, space-age materials. What do you think is its absolute #1 worst nightmare? What is the one thing that can bring that amazing piece of engineering to its knees?
Yep, you guessed it, uncontrolled heat. It's the silent killer of tool life, it's the top reason parts end up in the scrap bin, and let's be honest, it's a massive drain on your wallet. For today's explainer, this right here, this is our villain.
So here's our game plan. First, we're going to get to know the enemy, uncontrolled heat. Then, we'll dive into 3 killer strategies to fight back: high-efficiency milling, getting the cut right with climb milling, and using coolant the smart way. And finally, we'll pull it all together to see what true mastery looks like.
All right, first up, let's really understand our opponent. Now, here's the thing that trips a lot of people up. The goal isn't to eliminate heat. It's physically impossible. The real game, the pro move, is to manage it. Because when heat runs wild, you know what happens? Tools fail, parts warp, and you're just throwing money away. Getting this under control is step 1 to achieving those next-gen results.
So how do we start to manage it? Where do we even begin? Well, the first place to look is the actual path the tool takes, and that leads us straight to our first big strategy: high-efficiency milling. Seriously, this is all about working smarter, not just pushing the machine harder.
So what exactly is high-efficiency milling, or HEM? It's a roughing technique that completely flips the script on traditional methods. Instead of taking wide, shallow passes that only use the very tip of your tool, HEM does the exact opposite. You take a really small step to the side, that's your radial depth of cut, but a much deeper cut up and down, your axial depth. The result? You engage the entire length of the tool's cutting edge.
And you can see the difference so clearly here. On the left, with traditional roughing, all that insane, destructive heat is just getting slammed into one tiny corner of the tool. It's just brutal. But now, look at HEM on the right. That same thermal load gets spread out nice and even across the entire cutting edge. And what does that mean for you? Your tools last way, way longer, and you can start pushing your machine so much harder.
Now, the science that makes this all possible is a principle called chip thinning, and you absolutely have to get this right. It's the theory that lets HEM work so incredibly well. But, and this is a big but, there's a catch, a really dangerous one if you're not paying attention. And that catch is called the chip thinning trap. Think of it like this. If you try to slice a tomato by just pressing the knife straight down without sliding it, you're not cutting, you're just smashing it, right? It's the exact same idea here. If you reduce your sidestep for an HM toolpath, but you forget to dramatically increase your feed rate, your tool stops slicing and starts rubbing. And that rubbing creates a massive spike of friction and heat that will absolutely destroy your tool and your part in a blink of an eye. Okay, so we've got a smarter toolpath. That is a huge step. But believe it or not, that's only half the battle. Now we need to think about the direction of the cut itself. This brings us to a fundamental choice every machinist makes. Are you going to use climb milling or conventional milling? So what's the real difference? Well, with conventional milling, your cutter rotates against the direction you're feeding the material. It creates a chip that starts out thin and gets thicker. The problem is, this process pushes the heat back into your tool and into the workpiece itself. But with climb milling, the cutter rotates with the feed. It takes a big bite first, creating a chip that goes from thick to thin. And this one little detail is a complete game changer. Because with climb milling, all that destructive heat gets packed into the chip and then yeeted away from the cutting zone. It's brilliant. Just by making this one simple choice, you get a cleaner cut, way less rubbing, and you stop the tool from recutting old chips. The result is a dramatic improvement in tool life and a much more stable process, all because you are actively telling the heat exactly where you want it to go. All right, we've talked tool paths and cut direction, but what about the most obvious weapon against heat? Coolant. I mean, it seems simple enough. Just turn on the flood and let it rip, right? Well, in reality, coolant is a super powerful but often misunderstood tool. It can be a real double-edged sword. And that leads to the really common assumption. Is the solution to just flood everything with coolant? The more the better, right? Whoa, not so fast. Using coolant the wrong way can actually be worse than using none at all.
First, you risk thermal shock. Hitting a blazing hot cutting edge with cold liquid can cause microfractures in the tool. It's bad news. Second, the wrong pressure or delivery can literally snap a delicate tool. Third, and this is a big one, its most important job is often just to flush chips away, not even to cool the cut. And finally, that stuff is expensive. In many cases, a simple targeted blast of compressed air is the smarter and way cheaper solution.
So, let's tie all of these powerful strategies together. This is where we go from just using individual tactics to building a complete philosophy for mastering modern machining. So here it is, our playbook for heat control. For high-efficiency milling, the action is a low radial cut, a high axial cut, and, you can't forget this, a massive boost in your feed rate to spread the heat. For climb milling, you cut with the feed to eject that heat with the chip. And for coolant, it's about intelligent selection. You pick the right type and delivery for the job at hand. You don't just hit the flood button and hope for the best.
So, here's the real takeaway. Mastering heat isn't about tweaking a few settings in your CAM software. No way. It's about building a fundamentally smarter, more reliable, and more advanced manufacturing process right from the ground up. That is the definition of next-gen manufacturing.
And that leaves us with one final thought to chew on. As we get better and better at controlling this invisible force, it really begs the question, with heat truly under our command, what new materials, what incredible new speeds, and what complex geometries will finally become possible? The future is being machined as we speak.